Hello everyone, I'm Yang Cao from the University of Edinburgh. Thank you for checking out our work. This is our joint work with Shuai, also from Edinburgh. This work is about caching. Cache is used almost everywhere, like in our CPU and also our familiar database buffer pool. In such cases, cache is in the critical parts of our systems, and the computing logic can only read and write data through the cache, so it is also called inline caching. But there are also cases where cache is used as sort of a standalone site system, as an extension of our existing systems. For example, Facebook heavily used Memcache to augment their MyRocks database. Such cases are often called local site or simply a site cache. The main difference from inline caching is that a site cache doesn't talk with the main storage, for example, the database at all. Instead, database and cache individually communicate with the application server, and it is the application logic that coordinates the two. So a site cache is, to some extent, more flexible and dependable. For example, if we take a site cache out of the picture, the system still runs perfectly fine. So in this work, we focus on a site cache. The working logic of a site cache is pretty straightforward. For read request, the application server looks up in the cache first. If it is a hit, then everything is done. If it is a miss, then it simply fetches the requested item from the database first and then caches for future requests. A site cache doesn't really participate in the write logic. Instead, the application server commits updates to the database directly and then propagates the changes to the cache according to the cache invalidation protocols. So in essence, a site cache doesn't really implement any of the write logic. The only part it implements is the cache replacement policy to evict cache items when cache overflow happens. Here we focus on single thread cache or site cache in this work, as most caches don't have much concurrency control and often run in a single thread mode, like for example Redis. In traditional caching, each request touches only one item, for example, read item X or write item X. In this work, we consider slightly different requests. We consider requests that consist of multiple read operations or write operations. So this is somehow like transactions, and it is actually quite common for applications that use or site caches like web applications. For example, when we check out a Facebook page, it is in fact a read transaction that loads hundreds of items from Memcache. So that's a big read transaction. Often the answers to this sort of transactional read have to meet some semantic constraints. Two common ones are consistency and monotonicity. Consistency requires that each transaction must see a consistent view of the backend database, just like snapshot isolation. Monotonicity concerns multiple subsequent transactions. For example, if a read transaction observes the second version of a requested item X, then any subsequent read transaction must not see the older version 1 of X. So the observed change of X from version 1 to version 2 is not lost. So all this seems quite straightforward and somewhat irrelevant to catching. So why does it matter when we consider a single thread catch like Redis? There is no need for concurrency control and consistency should always hold. But this is in fact not the case for a side catch due to catch invalidation. I think it's appropriate to put this quote from Phil Carton, which is well known to a lot of system people. So he said there are only two hard things in computer science: catching, validation, and naming things. So again, here catching validation plays a critical role. So let's see how it makes things different for transactions. There are we can sort of classify catching validation method into two categories. The first class is for example, the TTL, time to live, and the ban invalidation method. TTL is essentially no invalidation at all. We bet on luck to set a correct timer on the catched items. The ban protocol is slightly better. It notifies the application server about the changes by the write operations to the database, but it is up to the application logic to decide the next step. They are both popular in practice since they don't degrade catch performance and are very lightweight. The other type of invalidation is to use purge or refresh protocols, which actively remove or update the changed items in the catch. They can always keep catch consistent with the database, but they put a very heavy toll on the catch performance. In addition, they are also hard to implement exactly in practice, so they mostly work in theory. In this work, we focus on the ban or TTL-based catches for transactional requests. We have actually studied purge and refresh invalidation in our previous study, and we have a generic technique there for dealing with multi-size transactional requests. In fact, as you can find in the paper, unit-size transaction is in fact more challenging and interesting from the technical point of view. Although the ban invalidation is practical and popular, it makes transactional catching more difficult. For example, so this is a toy example to show the difference. Suppose we have a database that holds Bob's record with his name, region, and address and phone number. And suppose we have Annie's sort of issue using three read transactions to look up Bob's profile. Suppose between request R1 and R3, Bob updates his profile using write transaction W2. Then the state of the database and catch changes like this. So initially database contains Bob as name, US as region, 111 and as phone number, and California as address. When Annie's reads transaction reads by transaction R1, she gets Bob UK California, and these are also catched. After W2, the database record becomes Bob UK 222 and London. By ban invalidation or TTL, a catch is not updated immediately. Then for R3, Alice could get Bob for name, US for region from the catch, but it will need to fetch phone number from the database, which is 222 now. So 222 is also stored in the catch. So the answer to R3 of the catch is inconsistent since the catched region US and the new phone number 222 are incompatible with each other. So there is never a point of time that the two values coexist in the database. So to rectify this, we can fetch region UK from the database to make R3 a consistent hit. Then we also store UK as a region in the cache as well. So for R4, name, region, and address are all in the cache, so it is a cache hit, which gives Bob US California as the answer. And it is consistent actually. But it is not monotonic since R3 already sees UK as region, but this consistent answer to R4 sees the older value US as region. So this shows a practical caching validation method can make caching for transactions challenging in maintaining those correctness guarantees. In fact, we have just given a naive solution in the example. We simply check whether the cache hit returns a consistent and monotonic answer to read transactions before returning the answer to the application server. But this comes with its issues. First, we need to somehow change existing caches in order to keep track of the updates for consistency and monotonicity checking. And even worse, this is somehow intertwined with the main job of the cache, which is cache replacement or eviction policy to deal with cache overflows. And this twisted connection can make LRU and existing cache policies much worse for transaction or transactional requests than for traditional requests. So in this work, we present a lightweight cache layer that can be used with existing cache systems such as Redis and Memcache to make them work well for transactional requests. It ensures that cache hits on Redis are always consistent and monotonic. It also provides cleverly designed monotonic consistent cache policies, and these policies can be used by the underlying cache systems such as Redis, so that they can enjoy better performance and with provable guarantees. And moreover, all these benefits come without the need for any modification. So the main technical meat of this work is about the design and analysis of transactional cache policies, depending on the knowledge of the cache request when we make cache action decisions upon cache overflows. We consider three input models: the batch model, where we process requests using a buffer so that we can process in batches, and the semi-online model, so we still do it in batches, but only the read transactions are known in the batch. The write transactions are not. They are coming on the fly, like the Redis secondary nodes, which receives, which can check the read request in the local buffer, but write requests are coming from the master node on the fly. And the online model is the most intuitive. So everything is unknown, is online, and we process requests one by one. We show that even for unit-size transactions that consist of items of the same size, for example, all items are integers. So under the batch model, the problem is already NP complete. As far as I know, this is very rare. Normally, multi-size requests are well known to be NP hard. That's not a big deal. We all know that, but not for unit-size cache requests, as they can be optimally processed in the batch model using the well-known validate policy. So despite this somewhat surprising list of complexity, we dig deeper and develop a few catch policies for transactions with provable guarantees. So in particular for the batch model, for depending on how we make how we treat the stale items in the catch when we make catch kit consistent. So we developed a provably optimal policy when we maximize the use of stale items in the catch, which we call the lazy version selection strategy. For the semi-online online model, we give theoretically competitive policies that can make use of a binary classifier. Moreover, they are machine learning robust in the sense that even the classifier works extremely bad, for example, making incorrect prediction for each and every classification request. The policy is still provably competitive. So we also deployed the catch system with the catch policies on top of Redis with HBase as the backend database. We tested the effectiveness of the policies in reducing the number of reads to HBase and the end-to-end transaction throughput improvements in EC2. The results are quite positive. Please check out the paper for more details. So, in summary, we have done several things that we think are interesting at the conceptual level, algorithm level, and also system level. Conceptually, we identified the problem of transactional catching for ban invalidation-based catches, which also works for TTL-based catches. We formulated the policy design problem, settle is complexity, and develop catch policies with provable performance bounds. On system side, we developed a catch middleware that can fit existing catches for transactional workloads and enjoy the performance boost with our transactional catch policies without changing a single line of code. So please check out the paper or contact the authors for more details. The proofs, the source code are all open source. So thank you.